Hi guys, this is Achyut. Uh, Today's topic is going to be stack. So we'll be discussing about the stack and what is a stack, and then what is the time complexity when we are doing operations on a stack, and what are the real world example for a stack, and what is the code implementation for the stack like push and then a top and is empty or other function. So stack in the sense, the word itself suggests that it is a stack. Suppose let's say it is a linear data structures in which the insertion of new element and removal of the element takes place at the same end, represented by top of the stack. Let's take this example. Suppose let's say this is a stack and we want to insert an element. Then we are going to insert at the top of the top end, and then when you want to remove the element from the stack, then we are going to remove from the top end itself. That means whatever we are inserting and then whatever we are deleting from the stack, it is going to be from one end only. So the real world example can be, let's say we have plates which are arranged in any hotel or anywhere. So they're going to be plates, and if you want to keep one plate on top of the other plate, so when we are putting the plate on top of another plates, it is going to be at the top end itself, and we are going to remove the plate from the bottom end. So if we consider, like, really we can take out all these we can lift this all the plates and then we can take the middle element. But when you come to real stack, we are going to do the operations on only top end, which is pushing and then popping off the element. Push in the sense we are putting the new element on top of the stack, and then when we are popping in the sense we are taking out the topmost item which is present in the stack. So that is the push and pop. And we can, if anyone asks you about what is the stack, you can just remember one particular statement, which is last in first out. So whatever the element which we had put last element, that is going to be first out. So we are going to take out that particular element from the stack. So that is stack, and then there are going to be different functions we are going to implement on one class of a stack. Those are going to be pushing the element and then popping the element and then getting the top element which is present in the stack, and then we are going to check if the stack is empty or not, and then we need to know whether what is the size of the stack. At present, what is the size of the stack? So pushing in the sense we are going to push the element, and then pop in the sense we are going to pop an element from the stack, and then top element will return top of the stack, and is empty is going to return if the stack is empty. So and then when we come to code implementation of a stack, we are going to implement here it is that get top index. Okay, so these are the functions we are going to implement in this particular class, which is going to be push, pop, and then is empty, get top index, and get element at particular index. And then if you want to write like int top, that is going to be uh, one more one more function. It is going to be int, like int top. As we have declared index as top, so we can take top element here. We can write this function as well. So this is going to be giving us the top element which is present in the stack. So let's see the implementation. So maximum size we can have in the stack is 100. Like, we are just mentioning the whatever size we want. We can mention in the code, like if you want 10 power 4, then we can mention here itself. So that is just a implementation. So when we come to the constructor, we are just declaring the top to -1, so that we'll track the index of top such that we can insert at that particular time. We'll just increment the top and then we are going to insert at that particular place. Suppose let's say we want to push an element, then we need to consider different cases. One of the cases, suppose let's say the stack is full, then we cannot push one more element on top of the stack. So that's why if the top is equal to maximum size minus 1, then we can say stack is overflowed. That means stack is full. And if the stack is not full, then we are going to increment the top to particular index, and then we are going to assign stack array of top is equal to whatever the element which is given, like we are pushing the element. So when we want to pop the element, they're going to be one case where the stack itself empty. So if the stack is empty, we cannot pop the element from the stack. So that's why we are going to say stack is empty or stack is underflow. So we are going to return -1. Suppose let's say the stack is not empty, then we are going to remove that particular element which is present. So we are going to decrement the top index and then we are going to return whatever the element which is present now as a top. Suppose let's say this is the element we have, and then if we pop this element, we are going to decrement this top to here, and then we are going to return this element. And then you want to check whether stack is empty or not. If the top is -1, then we can say that it is empty. Now if you want to get the top index, then it is going to be top itself. Why? Because when we are pushing the element, we are incrementing the top. When we are removing the element, we are decrementing the top. And then when we want a element at some particular point, then we are going to say stack array of some particular index. And then as we have wrote one more function which is int top element, it is in the class stack. So it is in the stack, and then we need to get the top element. Suppose let's say if top is -1, then we can say stack is empty and return -1. Otherwise we can return element which is present, which is stack array of top. So this is a function we are going to write for the top element. So and then if we see as we have seen in the implementation, let's discuss the time complexity for each one of the function. So if we see the function, when we are pushing the element, we are just pushing the element at the end. So the time complexity will be big O of 1. And when we are popping the element, we are popping the element by decrementing top -1. So it is going to be big O of 1. If we want to know whether the stack is empty or not, it is going to be of big O of 1 time complexity. For the size, as we know the top, we can know the size as well. Suppose let's say top is -1, then size is going to be, let's implement size as well. So stack size. So we are going to return top +1. So if it is -1, it is going to be 0. If it is 0, then the size is going to be 1. So that's why we are returning top +1. So that is the time complexity. And then yeah, that is the intuition. And then one more thing is, suppose whenever we are doing recursion, there will be a stack. Suppose when we run a function, so this is a first function we'll call, and then again one more function, and then again one more function, one more. So whatever the function we had called till now, thus functions will be stacked like this. And then whenever we are put we are putting one more function, we are going to append at the top itself, and then we are going to remove the function from the top itself. Suppose let me give an example. So this is one of the recursive solution which I had wrote. Suppose I'm just returning the sum of the elements which are present, sum of the natural numbers. Suppose let's say I call recursion 5. So recursion 5 is going to come here, and then we are going to add 5, and then it is going to call recursion 4, and then again here it is going to come and then add 4, and then it is going to call recursion 3. So it is calling again and again. So the recursion will be stacked here, like when we run. So if I run this particular function, we'll get to see the call stack. Yeah, let me show the call stack. Yeah, this is the call stack. Um, if you see carefully, here I added a breakpoint which is at the 16th line, and when we call this recursion 5, we are going to come here and then add 5, and then we are going to call again 4. Suppose let's say I continue, and then it goes to 4. So the recursion which is added now, it is going to be added here, right? So and then again, if I say continue again, it is going to add one more function at the top. So it is kind of a stack, call stack. We'll call it as call stack. And then suppose let's say if I remove this particular base case, then it is going to run again and again and again, and then it will be time limit exceeded, or it will throw like a stack overflow. It will throw like it is stack overflow. Why? Because we did not mention any base condition here to stop the function, call. So whenever we are writing any recursive solution, we need to take care that the function should end at some particular point. Why? Because we are calling the function again and again, so it should have the end so that it will stop at some particular time. Yeah, that is it for the stack, and then its operations, and then code implementation, and what will be the time complexity and everything. Yeah, thanks for watching. Have a nice day.